showing some of the main properties of these technologies and how these technologies can be combined and how this technology can be applied on real use cases. And clearly, it will be the future direction that we know some important challenges that we have to face today if we want to work with technology. I guess that the majority of you know what the blockchain is, or at least here this word at least was, and mainly the blockchain born with the Bitcoin mainly is a peer-to-peer payment system where the participants are able to exchange transactions sending what that are called cryptocurrency without the need of third-party intermediaries or the central authority attesting the validity of this transaction and what happened between the participants of the blockchain itself. Clearly, his technology today is it's known as a disruptive technology that mainly on the first instance is changing the payment system that we have today, but it's growing and the properties of this technology are going to change, and it can also be introduced in other sectors than the financial one. Basically, if we think about the blockchain, we have the main ingredient that are transaction, because in the blockchain, every participant has a so-called wallet that is composed by an address that identifies the user in the blockchain, and this address is tied to a private key that is used to sign a transaction that can be sent to other participants within the blockchain. These transactions are in some way grouped and stored within specific blocks that are marked with hash functions. And then when these blocks are formed, are linked together using this hash. And clearly, the process that allows to create a new block is called the consensus algorithm. That is a distributed algorithm that is empowered by the blockchain participant, with which they are able to create new blocks, and this process makes the blockchain going. Clearly, today the blockchain doesn't offer the blockchain technology doesn't offer only the exchange of cryptocurrencies, but the advent of the smart contracts completely changed the application of the blockchain and the meaning of the blockchain. And we know that since 2015, the Ethereum proposed the concept of a smart contract, that mainly you can think of a smart contract as a portion of code, a portion of software that is stored in a distributed environment in which everyone can interact with this portion of code, and this portion of code are executed by the majority of the nodes of the network, making the execution of the function contained in this smart contract as secure as possible. Clearly, today we have plenty of blockchains that they offer very different characteristics. For example, we have Ethereum that is the first one. We have Solana that is completely different from Ethereum, and clearly we can also choose the best blockchain that would fit for our needs. And the main benefits introducing blockchain into Industry 4.0 are certainly security and transparency, because being a distributed system, every participant are able to verify what happened, and clearly every transaction within the blockchain is marked using cryptographic primitives that are asymmetric digital signature for authentication and hash function for integrity. So clearly, the integration of the blockchain can enhance the decentralization of the system being based on a distributed network of different nodes. Clearly, one can using the blockchain, anyone is able to track the activities that are stored on the blockchain itself, enhancing, for example, the supply chain management. And clearly, the use of smart contracts can some way maximize the automation, for example, triggering the payments depending on some events or any other function that can be coded within smart contract. But clearly, even if the blockchain can bring some benefits, it brings also some challenges, because clearly we know that from the trilemma conjecture, we are not able to build systems that are at the same time distributed, secure, and scalable. And in fact, the blockchain maximizing the security and the distributed features sacrifices scalability, because we are not able to create systems that are at the same time scalable, secure, and distributed. The other one is interoperability, because the blockchain being based on different cryptographic primitives and different consensus algorithms. Each blockchain acts as an isolated environment. So today is difficult to make the blockchain interoperate with each other. And there is this one of my main research subject in finding interoperability solution that can be applied both in public and in private sectors. And the third one is, of course, latency, because the transaction in the blockchain must be validated by all the nodes composing the network, or at least the majority of the nodes composing the network, and clearly it prevents or makes it difficult to have real-time communication. So the other technology that is leading into Industry 4.0 is without doubt the digital twin. And in the last days, we had a different presentation about the digital twin. That basically, if we think about the digital twin, we think about in some way a virtual twin of a physical object. And during the years, the idea of the digital twin changed, both in what we can represent in a digital environment, but also in how can we interact, how can we create interaction between the physical object and the virtual object. And mainly, if we think about the digital twin, we have, of course, a physical object that today could be, for example, a good, a production system. And yesterday there was an example of the digital twin of a city, a vehicle, and today we can create a digital replica of whatever we want. And clearly we need a digital representation of this digital twin that must evolve with the digital, with the physical part. So this digital replica should have a number of functions that are used, for example, to conduct some forecast on the behavior of the physical part, or can be used, for example, to enhance the properties of the physical part. So mainly what that we need to conduct such kind of task is the link that, in my opinion, is the most important and the most delicate part of the digital twin, because the way in which we think about the interaction that the digital twin can have from the physical part, we can think about this link like one direction that is the majority of the application that we have today, for which the physical object is able to send messages to the digital object, which can change the behavior, can reflect the behavior of the physical one. But if we think about the opposite, for which the digital twin is able to change the behavior of the physical object, we cannot find a lot of works addressing such kind of feature. And it is quite understandable, as it is quite risky to allow digital software to change the behavior of the physical one, depending on the application. So clearly the benefits of integrated, at least the benefit also depends on the application and the kind of digital twin that one want to implement. In this case, maybe I'm focusing mainly on a manufacturing system. So if you think about the digital twin of a manufacturing system, we clearly have can monitor in real time what is happening during, for example, the production of an asset. And using this data, it's possible, for example, to make any kind of optimization from, for example, predictive maintenance or anomaly detection, or maybe we could be able to create defect-free product and so on. Clearly, using this massive amount of data, we are able also to improve the design of the product and the design also of the product process, maybe avoiding redundant phases or usually optimize the supply chain as well, understanding, for example, the demand and in some way have some forecast about the material that we need to build our products. And clearly, we have also challenges in the integration of the digital twin. And the first one, of course, is data management, because the digital twin somewhere rely on IoT sensor, and it is known that IoT sensor produce a massive amount of data, and the majority of which could be also unusable for a number of reasons. So one of the main challenges is to find good and fast solution for this for the management of this kind of data, especially because depending on the task that we want to conduct on this data, we need also costly hardware, and so we have to pay attention. Clearly, is also the security. Security is it is good by the fact that if we think about complex system, the number of IoT devices are if the number of IoT devices interconnected is high, it means that we are going to open to cyber attack risks, because these devices are constrained and clearly it's difficult to have IoT devices that are segregated in some way. And clearly, the security is much is not only in the communication between IoT to the digital twin, but if we think about the digital twin that are able to change the behavior of the physical system, we have to pay a lot of attention because it is very risky, and we have the risk to compromise a part of the entire system if, for example, the digital twin is compromised or acting maliciously. And finally, also the integration of the digital twin with legacy systems today, because there isn't in some way a common accepted definition of what a digital twin is, and at the same time there isn't today a standard requiring, for example, the design and development of digital twins, and it could make it difficult to integrate this technology in different systems. So having in mind these basic properties in some way, I would like to show you some applications that in some way in which those try to combine these two technologies in order to solve some challenges and introduce some benefits of this one. And the first work is based on the idea of a digital twin that can be shared and can be used by different people and different parties that potentially will not trust each other. And the idea of the author is mainly to understand the main phases for each, the main phases needed to build a digital twin and register on the blockchain each phases. In this way, at least the authors, in this way, the idea is to have a way for which every actor that needs to interact with the digital twin has the possibility to verify the building phases and decide, for example, to trust if the phase design was successful, if the phase was done in the proper way, if the test phase is maybe, for example, expensive, and then clearly the delivery process where the digital twin arrives to the final use. It is just an idea, but clearly we can think about more complex interaction between the digital twin and the blockchain, because in this way we are going to create some way a certificate of the creation process of the digital twin, but we can do, for example, more. And the author in this paper try to combine the digital twin and the blockchain to track the life cycle of the product. And In this case, for example, the author focused on the construction of a turbine, and they identified the phases from the design up to the recycle of the object. And the idea is to start to record on the blockchain every phases that are from the design, in which the designer starts to try to understand every component, how the components must be tied to each other. And clearly, after the design, we have the manufacturer phase where the design component start to be created. And after the clearly the manufacturer phase, we have the assembly phase where each component is assembled to create the final product that must be delivered to the final user. And clearly also they wanted to continue the monitoring of the product, also tracking, for example, the maintenance up to the recycle where possible. So the idea that we are using the blockchain in some way to verify the phases of an entire, to create the digital twin of an asset following the entire life of the asset itself. Clearly, the blockchain cannot be used to store every interaction with the digital twin, but maybe we can use the blockchain just to track some main events or some main actions that of significance for the application. Another approach is from the author of this work, in which they use the blockchain as a sharing medium for between interested parties. And the idea is if they propose the example of the digital twin of the construction phases of the project. And the idea is to clearly there are different actors in the construction of the construction sector. And the idea is that to track the phases of the project, maybe also during one day or with weekly or monthly. But the idea is to track every phase and store it on a blockchain that can be accessed and can be managed by different actors that could be also entrusted, maybe they could compare against each other, for which clearly we have the physical space where the sensor can maybe track the machines are going to be and are going to work, the virtual space that track each movement. And clearly the blockchain takes place to store some specific event in the construction phase, like for example the starting of this part of the project, the ending of this part of the project, and so on. And clearly this should in some way enhance the shareability and the trust of the digital twin. But and another idea in which we can use the blockchain that in my opinion could be even more interesting is that why we cannot use the blockchain as communication medium between the digital twin and the physical system. Because we saw that since the digital twin rely on IoT sensor devices, the communication are the risky part, also from the physical part to the digital one. So the idea is, if you think about the cyber physical factory, for example, where we have a number of sensors monitoring the task of the station on which they are tied. There are, for example, from the National Institute of Technology, a challenge raised in 2016 about the research of lightweight cryptography scheme for IoT sensor devices that ended in 2023. And they proposed about 10 different cryptographic schemes based on symmetric cryptography, for which today we could think about each sensor that can send silent messages to the digital counterpart. And this kind of cryptography clearly affects a little bit the delay of the communication, but is not too the performance are still good. So it's not is a feasible solution today. So the idea is to empower the IoT sensor with a lightweight programming scheme for which you send message to the digital counterpart. The digital counterpart is not a central software, but is a distributed software for which each device is trying to reach to its sensor. And the idea is how can we send the message back to the physical factory in order to maybe change the behavior in case of, for example, anomaly or in case of malfunctions, in order to prevent any damage or limit the damage if something bad is occurring. The idea is to, if we can also think about, okay, if the component D3 is detect that there is something bad on the sensor S3, you can just send a message saying stop your production, stop your activity because of. But if we are going to open the risk that the one single component of the digital twin is able to change the behavior of the physical system, maybe the action monitored by the sensor S3 could be tied to the action of other sensors. So a bad message to S3 could compromise other part of the physical system. So the idea is we can use a sort kind of consensus in the digital twin that is distributed in some way, but we do not want that this kind of message is verified directly by the IoT sensor, even because maybe they haven't the computational power to decode the complex cryptographic primitives like a Traceability scheme. So the idea is that as soon as the D3 part detects that there is something bad happening in the physical factory, he must ask to the other digital counterpart if they recognize the same event. And using a Traceability scheme, they send a transaction to the blockchain. And in the blockchain, we have a verification code that is in charge to verify the transaction signed by all the digital twin components. And clearly, if the verification passes, there is a configuration code that stores all the configuration of the physical factory. That is, for example, can be the speed of the belt line, can be, for example, the heating of the pressure of the heating treatment, the pressure to be applied to the pressure treatment. And if this kind of event is detected by the physical system, it means that that event cannot be tampered with because it's the output of the blockchain computation. So there is no way to alter because every party is able to detect that event because it's just part is accessible by every part of the digital twin. So it means that once the S3 changes its behavior with respect to the normal one, the digital twin is able to read the message that changed with respect to the normal behavior and can verify if this kind of transaction happened. And not only the D3, all the digital twin are able to detect such kind of this change of configuration. So, and it could be something for which we could think about the actuation for which we can build digital software that are able to automatically manage the physical device, also for tasks that are not just to turn out the light, but also maybe if we think of complex application like healthcare or smart cities, we could have a number of applications that could be feasible. Clearly, the risk still, we still have some risk, but in this way we are going to maximize as much as possible the security of this kind of functionality. And clearly, if we think about the malfunction and anomalies, we haven't discovered the problem because we know that there are cases, but and so to understand the security of the approach, we are in some way verifying the latency in the communication between the digital twin to the physical system to understand how long does it take to create the transaction, validate this transaction, and make the change of the behavior. And Usually, on a basis of 5,000 transactions, we can see that the average latency is between 0.6 and 0.7 seconds. That is less than 1 second. That is even better than a human intervention. That in some way should be slower than the physical skills. And finally, clearly, integrating blockchain digital twin at the same time is not at all easy because there are some open challenges that are not covered. And for example, one of the main problems is that the blockchain that today we have are very different from each other in different properties that are, for example, in the consensus algorithms, in the cryptographic primitives, in the language for smart contract development. And so it is not easy at all to integrate such kind of platform with other system, specifically also because we have a standard for smart contract development. It means that, for example, that if we develop a solution using Ethereum, for example, it's not so easy to create the same solution using other platforms, offering, for example, different smart contracts with different properties. So one thing that we could do, for example, is at least create a standardization of smart contracts, for which we have some way models, or we have languages that are quite similar to each other, for which it is easy to translate the solution in one blockchain to another one. And clearly, we have also a lack of unified data models for what concerns digital twin, because today I think the application of the digital twin in different sectors that are, for example, healthcare, manufacturing systems, smart city, all these sectors have mainly different needs and different properties for which the solution that we are going to codify in the digital twin could be very different from each other. And at the same time, it makes it difficult to integrate the blockchain in all of these different situations. Also goes because we have a different rate of synchronization and different kind of fidelity of the digital twin with respect to the physical object that we are going to address. And finally, clearly, is the lack of an ontology or a semantic standards that can be helpful both for design digital twin, but also to think about the blockchain integration for such use cases. And also, for example, if we think about the ontology not only on the, for example, digital twin models, but also in the interoperability within a different system, we clearly could have some way, an easy way to integrate such kind of technologies. I thank you very much for your attention.
Thank you, Alessandro. Any questions from the audience?
Thank you very much for a very interesting presentation. You just mentioned that this problem with these different languages of the smart contracts for the blockchain. From what from what I gather, is the solidity is quite like in many parts of at least for software engineering kind of type applications. It's a language which is quite, I don't know, maybe becoming standard, or at least is quite popular with a lot of people. And I wonder, is this something you've looked at, this solidity language at all, the Ethereum smart contract language, or is it something which actually doesn't fit at all the kind of things you would like to model?
Well, I personally love Ethereum, I love Solidity. A lot of blockchains today are going to adopt Solidity as layer 2 smart contract solution because Solidity was amazing, because like Buterin talked about everything when he proposed the smart contract. Within Solidity, we can find not only Solidity that is the language, but also the structure as low level, mid, and high, for which we are able to write a library in Solidity that are optimized by a computational point of view, but also offer higher level interface with which you can interact. There are also a lot of standards within Solidity for the representation of what are called token, to which we can create different cryptocurrencies, or what are called non-fungible token like NFT, with which we can create NFT. The problem is that Solidity is not the only language today, and there are a lot of different blockchains, specifically also for private sector, like Hyperledger Fabric, that is not based on Solidity. It is not based on NVM. So the problem is, since Hyperledger Fabric is much more faster than Hyperledger Bezo, that is the derivable machine for companies in some way. On Hyperledger Fabric, we can write smart contract on Java with Java, JavaScript, Golang. The problem is, are we able to, for example, translate the ERC20 standard of Ethereum into Java? How can we able to say these standards are the same, these smart contracts are the same? For example, if we want to exchange an NFT between two companies that one implement Hyperledger Bezo and one implement Hyperledger Fabric. That's why we need in some way also an ontology, for example, because for me it's quite easy. If we have a Java class targeting all the properties of the ERC20, for me it's easy. It is the same ERC20, but we are not sure about it. And clearly, the testing for vulnerability and other things could not, the outcome of this test could be surprising. So I think that this part of the report requires further analysis and further research.
In terms of, you mentioned that yes, latency and other aspects are an issue when it comes to deploying blockchain and the two counterparts, the physical and the digital twin. But what of also in terms of computational complexity of the entire system? At what level does it get increased? Take a scenario where you have an industry which is, let's say, car manufacturing, with number of islands, number of stations, on each station there are more than 20, 30 odd sensors. If you look at the number of sensors as they increase, where do we see this deployment that you have?
Yeah, it depends on what you want to store on the blockchain. Clearly, we are not able to store every message from the sensor on the blockchain because it's not easy. At the same time, we can ask ourselves, do we need every message to be stored on the blockchain? Because the idea is, if we use the blockchain as a medium to track some main events or some specific events, so we can mitigate in some way the problem of discovery of the blockchain. But it's not the only solution, because we could also accept the fact that we cannot use blockchain communication, but at the same time, there are some solutions called the layer 2 solutions in which here we can combine off-chain technology with on-chain technology to mitigate the starting problem. For example, we can think about the construction of a product that would involve a lot of sensors, a lot of data, stored in a distributed database, for example, and then store on the blockchain just the file to that data, and that clearly can be segregated then with hash list. And clearly, since we have the panel on the blockchain, we are able to.
Does that fulfill the purpose of traceability as well at the same time, or not?
Yeah, but clearly you cannot track every transaction. You can track the process. So that is, you can track the start and the end. The transaction is still off chain, so you are going to take a different certificate of chain where for each transaction you have to respect the hash, you have the hash of the process, and use the blockchain just to track that hash is completed. And it's fine. You can store the hash on the blockchain. You can verify that the data as the same hash. It's not compromised. But clearly, you cannot store all that data on the blockchain.
That is also recorded. Is it possible to reduce the this bar here to a single one, so that we can also see a bit more of the screen?